In the next three examples, we want to look at combining multiple log properties in order to solve some log equations. In example 12, we have the natural log of x plus 9 equal to the natural log of x plus the natural log of 9. We can't solve this the way we did in the previous examples because on the right-hand side we don't have a single logarithm. We have two logs being added together. But we know that with properties of logs, we can condense that into the natural log of x times 9, or just reordering that, 9 times x. Since we were adding those two together, we can multiply those two expressions together inside a single logarithm. Since the logs are the same base, we can set the expressions inside them equal to each other, giving us x plus 9 is equal to 9x. Subtracting x from both sides will give us 9 is equal to 8x, or x is equal to 9/8, 9 over 8. Looking back at the original expression, we need to make sure that x plus 9 is greater than 0 when we use this value for x, and that x is greater than 0. It's easy to see that 9 over 8 is greater than 0, so that checks out. Now we plug in x equals 9/8 into the other expression. Doesn't really matter what that would come out to be. We're taking a positive number plus a positive number. That's going to come out to be something positive, so that checks out. Since the value that we came up with is within the domain for each of those original log expressions, x equals 9/8 is a valid solution. Similarly, in example 13, we first need to condense the two expressions on the left-hand side. This will be the natural log of x times x minus 3 is equal to the natural log of 4x, which means we can set these two expressions on the inside equal to each other. The first thing we'll need to do is expand what we have on the left-hand side. This will become x squared minus 3x, and then we can subtract 4x from the other side to set this equal to 0. That will leave us with x squared minus 7x is equal to 0. And then we can factor out the greatest common factor of x to get x times x minus 7 is equal to 0. This gives us two solutions, x equals 0 and positive 7. Then we need to check these against each of the original logarithms. So the first one is just the natural log of x, so we need our value for x to be greater than 0. Our first solution of 0 is not greater than 0, so that already fails. We'll throw that out. Then we just need to check 7. 7 is greater than 0, but we also need to check that x minus 3 is greater than 0. 7 minus 3 will be greater than 0, so that checks out. And then we need to check that 4 times x is greater than 0. 4 times 7 will indeed be greater than 0, so that checks out. X equals 7 is within the domain for all three of the log statements. 0 is not, so we only have a single solution, which would be x equals 7. In example 14, now we have two log statements on the left-hand side that are being subtracted from each other. We can condense those together using division to get the log base 10 of x minus 2 over x is equal to the log base 10 of 4. Since the bases are the same, this tells us that x minus 2 over x has to be equal to 4. Multiplying both sides by x gives us x minus 2 is equal to 4x. Now we can subtract x from both sides to get negative 2 is equal to 3x. or x is equal to negative 2/3 as a possible solution. We have two different log statements with a variable to check. I'm going to start off with the log of x, meaning x needs to be greater than 0, because it's pretty easy to see that negative 2/3 is not greater than 0. So we have an extraneous solution, a solution that's not within the domain of each of the original log expressions. So here we would say D and E does not exist or no solution exists.